Hi, my name is Tapio Kramer from Incron. Today I'd like to talk about complex dynamic behavior of automotive electronics. In the part 1 of my presentations, I will explain to you the event chains that help you to understand the dynamic behavior of your software in the electronic components. If you want to ensure things work properly, you have to know what's going on inside. This is often a challenge when it comes to dynamic systems. You have to understand the dynamics. It is very helpful if you can take a look from different perspectives, if you can stop and replay, zoom in and out, and if you can perform what-if analyses. Especially if the task is performed by multiple resources that have to perform in time and in a coordinated fashion. Watching from different perspectives gives you new insights and new possibilities to optimize. What is commonly available to trainers and players of sports games is now possible in the development of dynamic automotive electronic systems as well. Today's driver assistance systems are built from highly networked systems, often with 10 or more ECUs involved. Some functions are co-located in the instrument cluster, others reside in ECUs like the braking system. Here we want to discuss an emergency braking assistance function. On the left we see the radar sensor connected to the driver assistant ECU. This ECU passes information to other ECUs over CAN, and in this case behind a gateway over FlexRay to the braking system ECU with the ESP and ABS functionality. Every involved party has different perspectives and responsibilities. The Tier 1 focus on their ECU and the OEM focuses on the bus communication. The emergency brake system can be described as a function network, as we see here, a bit simplified. Internally, every function block is a bit more complex for sure. But there is the hard deadline from radar to brake to meet under all circumstances. The OEM has in early system architecture phase the task to map all functions onto the planned hardware platform. Often the function blocks are distributed and communicate over bus systems. One major task is to map the blocks in a way that in the end will ensure the timing requirement of 300 milliseconds can be met. The latency of the end-to-end event chain comprises of many fragments with own latencies. As we see, the data flows through the hardware and function network. Wouldn't it be good engineering practice to validate even before the bidding phase that the planned event chains and latencies in the end will result in a performance system always keeping the 300 millisecond deadline? But how could the OEM define the event chain details and the timing without having the insight into the ECU from his Tier 1? And the different suppliers also have a restricted view to the overall timing, since they cover a subset of the functions only. Still, they have to meet the given deadline for their event chain part. But that isn't all what challenges the Tier 1s. Today's ECUs perform multiple functions, sometimes aggregated into domain controllers. The functions come from various suppliers, some competitors, some from the OEM, acting as a Tier 2 supplier in this case. Often, late in the process, when all functions have been integrated into the ECU, the tests reveal complex timing problems. The more complex the system is, the more possibilities for unwanted dependencies and interferences occur and end in hard-to-find dynamic behavior errors. Wouldn't it be nice if each party had timing and performance requirements to develop against? Requirements that are pre-validated? The architect could derive an architecture robust and reliable to execute all the integrated functions. The data flow through such a system is highly complex and dynamic. Every execution unit and communication channel influences the timing and therefore the end-to-end latency. Let's take a look at the subcomponent of the event chain in the driver assistance system. Here we see an event chain diagram from the real-time simulator CronSim. We can see all steps of the event chain where the data is processed and passed to the next function block or bus communication. And we can observe on the timeline on the x-axis that some steps take longer than others. We can measure the latency. But there are multiple executions of the event chain, and they are started every 50 milliseconds by the next radar sensor data package. Multiple instances of the event chains are executed in parallel. How are we doing regarding the deadline of the 250 milliseconds? Whoops! There is a case where we take too long. And what's there? A data packet is not processed further. What if this packet contained the decision perform emergency brake function? To understand better what's going on, we need another perspective, a more detailed diagram. In the task state diagram, we can now see also the tasks and interrupt states over time. Blue reflects the execution of the task, green shows when it was preempted and had to wait for the higher priority task to complete. So we see the event chain completion was delayed due to the higher priority task on the same ECU. And the broken event chain, the data loss occurs because of drifting clocks from the multiple CPUs involved here. That's mean. The time-triggered task executed a bit too early. Such kind of sporadic errors we often see in our customers' projects. That's why we always analyze this effect of drifting clocks as a default. Finding and understanding such errors on real hardware is a nightmare. From the OEM's perspective, the event chains begin at the bus interface. Here we see how the data flows now not only through the driver assistance ECU, but also over the CAN and FlexRay bus end to end. In the shown event chain diagram, you easily see where more or less time along the event chain is spent, where the segment lines are tilted more. Function blocks or communication steps causing irregular or late latencies are easy to find. And using other perspectives, digging into details with other diagrams, the cause for the delay is fast identified and sometimes even avoided. Maybe a sporadic burst of CAN messages caused a burst of interrupts and made our function block execute too late to use the actual data. This was part 1 of my short presentation about understanding the dynamic behavior in complex automotive electronic systems using the event chains. In part 2, you will learn how a better collaboration among the OEM and the suppliers teams will ensure robust and reliable execution of the functions. Thank you.